In this last section of chapter 10, we are in 10.3, and we're talking about space figures, three-dimensional things. And so the overview terminology, again, there is a bit of terminology. We're talking about planes, polyhedra, regular polyhedra, semi-regular polyhedra, pyramids, prisms, cones, cylinders, and then spheres, and some of the associated terminology with those things. Now, before we get too far in, I do want to point your attention to a couple different links. These are in your Blackboard course, and they are great digital applications to really examine three-dimensional and two-dimensional figures, geometric figures, if you don't have manipulatives. And even if you do, some of this stuff that these can do is pretty interesting. So here's one of them, pattern shapes. And this is, you can drag all these figures all you want. There was an opening challenge that you had to do in the very first video, and this is a useful tool for doing some of those things. What you'll notice here is a hexagon, a regular hexagon that should look familiar to you from the previous video, but it actually covered it in triangles, because remember we talked about the central angles and how you can divide things up into triangles. And so that is just a useful tool to show how you can build certain figures out of triangles and other things. And it's just a nice little manipulative, online manipulative place. The other thing is this isometric drawing tool. And here you are able to place within this grid all sorts of figures, cubes, and just different planes. So I can't place an object there or there. How about here? Maybe it's because I've already created this three-dimensional world. So I did create this three-dimensional figure. One of the fun things is you could actually rotate it. You can rotate it around. You can add to it, right? So I can add layers to this, and then I can rotate it and see what it looks like that way. You can even see, so these got these axes, right? You can rotate it different ways. If you just want to rotate it in one direction, you can. And this helps you sometimes really see a figure that you couldn't picture if it was just sitting on a page in front of you. And you can change it between two-dimensional. So the figure that I was just showing you, here's what it looks like from the front, from the top, from the right, and what we call its matte. Here it is back in three-dimensional figure again. And so if you're just looking at it from one dimension, that's that 2D top. And so that's a really nice thing to play around with. And so that actually leads me to sort of a challenge question that we're going to start with. And it's, imagine this figure that I have right here, right? And it has 54 small cubes in it. You could calculate that by multiplying the length by the width by the height of this, but there are 54 small cubes. And I want you to imagine if you had to paint this, if this was a box and you painted it all the way around, right? So you painted it all the way around. And then you were able to disassemble all of these little individual cubes. The question to you is, how many of the cubes would have paint on just one of its faces? How many would have paint on two of its faces, three of its faces, and none of its faces? And that is actually our start to our conversation. So there you can see the questions. And I would recommend you take a moment to just pause and see if you can figure that out. I think this is a great activity to start with because it gets you thinking three-dimensionally, trying to picture what's inside this diagram here. And so let's figure this out. And maybe you even go into that app that I just showed you. And by pulling it around, in some ways, you're almost able to see it better than if it's just sitting on a page here. So let's just start and say how many of the sides will have paint on one face. So that would be, if I'm looking at the top, it would be this one, this one, this one, and this one, right? The rest of that cube is buried inside. Now, those 4 are repeated here, they're repeated here, they're repeated on this back and on the bottom. So that's 16 so far. I also have 1 on this end and 1 on the other end. So that's 2 more. And so that's a total of 18. Now let's look at the ones that would have paint on 2 of their faces. Well, that's going to be, if I look at these 4 to start, 1, 2, there's 2 faces, the rest are covered. There's another one, there's another one, there's another one. So that's 4. I'm also going to have these 4, these 4, and the 4 in the back and the bottom that I can't see. So again, that is 16. If I look at this front part, I've got 1 here, 1 here, 1 there, and 1 there. So that's 4, and then another 4 on the back. So that's 8. So that's 24 that have paint on 2 faces. Now let's look at 3 faces. That's going to be the corners. 1, 2, 3, 4, and then another 4 on the back for a total of 8. And then none. We're the ones that are not going to get painted at all. They're on the inside of this figure. They're right beneath these 4. 1, 2, 3, 4. It's right behind this one. And there's only 1 layer. So it's the 4 that are beneath these 4 right here. And so that is 4. Let's double check. 18 plus 24 is 42, plus 8 is 50, plus 4 is 54. So going through that exercise helps you think 3-dimensionally. And that will help you when you have to start doing some calculations with volume. So let's move on and talk about some different aspects of 3 figures in space. But we're going to start the conversation talking again about planes, because we talked about planes before, flat surfaces, you could make it with your hand. And we know that in 2 dimensions, figures like lines and angles and polygons are on a flat plane, right? You can draw them on a sheet of paper. But in 3 dimensions, there are actually an infinite number of planes. Put your hand out and then put your hand on top of that. That's 2 planes. And then you keep taking your hand off, right? Every time you stack a sheet of paper, you're putting another plane. And in 3-dimensional space, if we look at a couple different things that happen, one thing you'll see here is on figure A, those 2 planes are parallel, right? Again, put your hand out in the air and put your other hand hovering above it. They're flat, right? They're never going to cross, no matter how far you extend them around. Those are parallel planes. You can also have planes that intersect. If you take your one hand and put it sideways and then intersect your fingers, interlace them like that, right? You've now made 2 intersecting planes. And note that on figure B, the place where those 2 planes intersects actually makes this line. So the intersection of 2 planes in space is a line. Now, we can look at the angles that are made when planes intersect. They're called dihedral angles. And they might look something like this. Just like with regular angles or with triangles, we can have right dihedral angles. Again, these are dihedral angles where planes intersect. You can have a right dihedral angle. You can have an obtuse, because it's more than 90 degrees. And you can have an acute dihedral angle, right? Imagine opening a book and shutting a book, right? That's how you can think of these dihedral angles. We can also examine how lines and planes play with each other in 3-dimensional space. Take your hand again, put it out in front of you. Now take your finger from your other hand and place it directly above your hand. So a line can be parallel to a plane, just like you see on your screen, if that line and plane never intersect each other, right? And so the plane goes flat forever, the line goes flat forever. It's kind of like an airplane flying over the ground at the same altitude. And so we can have a line M that's parallel to the plane P. In another scenario, we can look at a line that's perpendicular to a plane. So here we have plane Q. We've got, it's called Q right there. And then we have line N right here. And line N is going straight up and down. Notice this right angle there and this right angle there. So line N is perpendicular to plane Q because it goes right through it at a 90-degree angle. Imagine a telephone pole going straight down into the ground. Now, polyhedra, what is that word all about? We're going to spend a lot of time talking about polyhedra. So we'll start with a little picture of a real life object, right? This rock. What do you notice about this rock here, right? So here we have a crystal embedded in this rock. It's a three-dimensional object, and it has flat sides. And so this happens to be it's got 12 pentagonal sides. These are interesting because these are things that actually occur in nature, okay? And so this is a three-dimensional object with flat sides, okay? That's what a polyhedra is. Three-dimensional object with flat sides. And again, we can see this one embedded right in rock. And I think it's fascinating that those sorts of figures actually occur naturally. The surface of a figure in space, whose sides are these polygonal regions, again, are called a polyhedron, right? So we look at the singular form, and polyhedra is the plural. Now, the flat spaces that we see right there, those are called the faces of the polyhedron, and they intersect at the edges, and where all the edges meet are called the vertices. So again, this is a face. This right here is going to be our edge. And where two edges, actually three edges intersect, that's going to be a vertex. Or again, plurals, vertices. And the polyhedron itself is just the exterior, but when we combine it or look at the union of all of its interior, then we call it a solid. So that is an interesting fact that not a lot of people recognize. When you do look at three-dimensional figures, if you are talking about the polyhedra, again, it's just talking about the outside, right? The shell, if you will. Once you look at the interior as well, then it's called a solid. So here are three pictures. And my question to you is, those three pictures, which of them is or which of them are a polyhedra? Or are all of them? Or are none of them? Which might be a polyhedron? So if we go back to how we described it, polyhedron has to have flat sides. Flat sides. So what does that rule out? It rules out B, right? This is a sphere, doesn't have flat sides. So that doesn't have polygonal sides. On the right-hand side, this part C, this is also not a polyhedron because it has faces that are not polygons. Remember, these have to be simple closed curves. That's not a simple closed curve, and so that also is not a polyhedron. But part A is. All of its faces are flat polygons. It's made up of squares and triangles. Now we can also talk about, just like we did before with two-dimensional figures, with three-dimensional figures, we can talk about concave and convex, right? They can have these different characteristics. And so take a look at these three figures. Let's state whether or not you believe they are concave or convex based on what we learned before. Only one of them is convex, and that is number 2. This is convex. Why? Because we can see it caves in on it. I'm sorry, concave. I said that wrong, I apologize. Concave. Only one of them is concave because it caves in on itself. Remember how we looked at 2 points, and if we draw a line between those 2 points, if that goes outside of the figure, then it's concave. Get that right this time, sorry. These two are convex because they're only going outward. They're only going outward. Now, just like we had regular polygons where basically everything's the same, right? All the sides are the same and all the angles are the same. We can also have regular polyhedra. And so there are several that are well known, and they are these 6. And these are actually called, they call them the Platonic solids. I'll write that, Platonic solids. And these are the best known of all polyhedra. These 6 or these 5 regular polyhedra. So what does that mean? It means that every face is a congruent regular polygon, and the same number of which meet at each vertex. Okay, a regular polyhedron is a convex polyhedron whose faces are congruent. Let's talk about that part, right? This right here is a cube. That face, that face, that face, and all the other faces are identical, which means they are congruent. They are the exact same size and shape. And there are the same number of which meet at each vertex, meaning at that vertex, there are 1, 2, 3 polygons that meet at that vertex. And that's going to be the same for every vertex on that cube. The same applies for all of those. And the ancient Greeks proved that there are only 5 of those that exist. And these have names. So let me introduce you to those names. All right, so let's make this a little easier to read. So they are the tetrahedron. So that is 4 triangles for faces. So that figure right there is called a tetrahedron. The cube, we know, that's probably the most common. 6 square faces. Octahedron, right here, has 8 triangular faces. A dodecahedron has 12 pentagons. So each of those is having 5 sides, 12 pentagons for faces. And the icosahedron has 20 triangular faces. So there are triangles, and there are 20 of them that make up that figure. Now, the first 4 of those occur regularly in nature. We already saw one of them. We saw this one earlier. But now we also introduce these 2, right? So these occur often in crystals, again, which that just fascinates me. So those are regular polyhedron. We also have something called semi-regular polyhedron. And semi-regular polyhedron have 2 or more different types of regular polygons for faces. Again, this is something that can also occur in nature. So what do we notice here? This has a hexagon in front, and it also has a hexagon here, but its other side has squares. So it's made up of squares and hexagon. So we can define a semi-regular polyhedra as polyhedra whose faces are 2 or more regular polygons with the same arrangement around the vertex, or same arrangement of polygons around each vertex. And so they can look something like this. Here are a few different examples of those. Right, you'll notice hexagons and pentagons. I think this is octagons, 1, 2, 3, maybe not 1, 2, 3, 4, 5. No, that's decagons and triangles, squares and triangles. This looks like it's the octagons, 1, 2, 3, 4, 5, 6, 7, 8, and triangles, octagons and triangles, right? So those are really interesting combinations that can also be used for various building structures. So let's get to some that you're probably a little more familiar with. Let's talk about pyramids to start. So now when most people think of pyramids, they think of Egypt, right? The Great Pyramids. And the pyramids that were built in Egypt have square bases. I'm going to draw a very poor pyramid, square bases, and they rise up to meet at a point at the top, and all the sides are triangles. Now, you can have a pyramid with really any polygon as its base. Again, the pyramids in Egypt, that base down there at the very bottom of it is a square. But you can have triangles, you can have pentagons, but again, the sides, the key for a pyramid is the sides are triangular of a pyramid. And the way we name a pyramid is by the shape of its base. This is a square pyramid. At the top of churches, sometimes you will see a spire that looks something like this. And if you look carefully at that picture, you'll see that that is a triangle right there. It's going to be hard for me to trace that, but that is one big triangle, very tall, very narrow. And that is often those will be hexagonal or octagonal pyramids because they're made up of multiple six or eight triangles around the side. So if we could see the base of this figure, it would be a hexagon or an octagon. And so again, pyramids have to have triangular sides. Now, there are a couple different ways that pyramids can be shaped. Often we think of them or what are called right pyramids, but you can also have what are called oblique pyramids. So think about what you know about right angles, right? Think about what you know about right angles. Right angles, what does that mean? It means they meet at a 90-degree angle. And so if you look at these four examples of pyramids, three of them, numbers 1 and 3 and 4, excuse me, are what we call right pyramids because you can draw from the center of the base straight up to the top a right angle. Number 2 here is what we call oblique. And you can tell because it's leaning a little bit to the right. If you drop a line straight down from the vertex at the top, or the vertex of a pyramid is also called its apex. Apex meaning top. So the vertex on top is called the apex. It doesn't hit the center. It doesn't hit the center of the base, right? So that is what we call a right pyramid. Now, another feature of those right pyramids is that all of the sides are going to be isosceles triangles. So if you look at the sides of these, all of the lengths of the sides are equal in all of these other pyramids. But in this one, those sides are not equal. This side over here is longer than that side. Okay, so again, it's sort of shifted off to the side. So we have right pyramids and we have oblique pyramids. Next, we will talk about prisms. So this is another type of polyhedron. And here are several examples of common prisms. And so what I want you to do is actually pause and just stare at those for a moment and say, what do we think describes a prism? What makes it a prism? What's the defining feature of a prism? So the defining feature of a prism is that it has two parallel bases. Take a look at the triangular prism over here on the left. It has a triangle on top, and it has a triangle on the bottom. They're both lie in two separate planes, and they are parallel to each other. This quadrilateral prism, same thing. It has a quadrilateral on this side, on top, and then another one on the bottom. So it has a upper and a lower base, and they are congruent, two parallel bases, and they also have to be congruent to each other. So those are identical quadrilateral. These are identical hexagons. Rectangular prism is probably the most common. It's just a regular box, right? It has a rectangle on the bottom and a rectangle on the top. Now, like pyramids, they get their names from the shape of their bases, as we can see. Pentagonal prism, hexagonal prism, quadrilateral prism. And just like pyramids, they can, if the, you can have a right prism as well, right? So do we see any ones that would be considered right, meaning they're going to meet at a 90-degree angle, right? The lateral side is perpendicular to the base. So to me, those all look like right prisms. This one, again, does not meet at a right angle there. That is not a right angle. And so this would be considered oblique, right? It looks like it's sort of leaning to the side, correct? If we, like before, consider the interior along with our prism, then it would be considered a solid. So let's examine our prism just a little bit more and ask a few different questions. So what we see here is a right prism, and it has bases that are regular pentagons. So take a moment and answer these three questions, and note that the way we would label a face, meaning one of the flat sides, is with the letters at each vertex. So take a moment and see if you can answer those questions. So this is a bit of a callback from previous video. It says, what is the measure of the dihedral angle between face ABGF? Well, where's that? ABGF. So that's this face over here, and face BCHG. So that is BCHG. So it's asking the measure of the angle between this face here and this face there. It will be the same angle if we could look from above of this angle of that figure. What is that figure? It's a regular pentagon. Do you remember how to find the angle measure of a regular polygon? We take the number of sides, we subtract 2, and we take that number times 180 degrees to get the total angle measure of the pentagon, 540, and then divide that by the number of angles. That was 108 degrees. We actually looked at that one in a previous video. So for question number 1, that is the measure of the dihedral angle along this entire line between those two faces. They would meet at a 108-degree angle. Question number 2, what's the measure of the dihedral angle between face GHIJF? Where's that? GHIJF. That's this upper base. And face CDIH. That one is right here, CDIH. So that's looking along this line right there. So it's looking at what is this, how does this face compare to this face, and what's the angle between them? Because it's a right prism, they are meeting at a right angle. Imagine a box with a lid and its side, they're going to meet at a 90-degree angle. So that one is 90 degrees. Then it says name two faces that are in parallel planes. Well, that's going to be this upper base and this lower base. So side A, B, C, D, E, and side F, G, H, I, J. Okay, so there's a little analysis of some polyhedra. Again, these things do occur naturally, which I think is pretty fascinating. Those are two oblique hexagonal prisms that are crystals, and they grow like just like that. The next one we'll look at is a cone. So cones are kind of similar to pyramids in a way, except they have circular bases. Right? So a cone is going to look like this. And just like before, we can have right cones and we can have oblique cones. Right cones, again, if you drop a line straight from the vertex point or the apex, it's going to hit right down in the middle, the center of that base. Oblique will not. It has a base that's a circle or a disc. They have vertex points called the apex. And again, like I said, we can have right or oblique cones. Next, we have the cylinder. A cylinder, very similar to the cone, except it's got circular bases on the top and the bottom. So both the upper base and the lower base will be circles. You can have right cylinders, you can have oblique cylinders. And then finally, we have spheres. And spheres are generally think of like a ball, right? Or the Earth is very close to pretty close to a sphere. It's not a perfect sphere, but it's very close. But if you remember earlier in the video, I mentioned that all of these polyhedra are really just talking about the outer shells. And if we consider the interior, then they become a solid. But often we're just thinking about the exterior, like a box. And so if we think about a sphere the same way, it actually has a pretty interesting definition. And so I'm going to post this definition for you to read along with me. It says a sphere is the set of points. There's that word we introduced way back at the beginning of the course, a set, right? A group of all of these points. It's a set of points in space that are the same distance from a fixed point called the center. The union of a sphere and its interior is called a solid sphere. So isn't that an interesting definition? Imagine if you could travel all the way to the center of the Earth. And actually, let me see if I can draw a sphere. All right, so you start with a circle, and then you sketch a line around this way, and then sort of a dotted line around the back. So there's a sphere. And imagine I could place a point in the middle of that circle that I just drew. And then I took and I measured how far it is from here to the edge of that circle there, or to the top of my sphere, or to just some other random point, right? So this is going to be the exact same dimension to every single point on the exterior of that sphere. That's what a sphere is. Now, just like with a circle, a line segment that joins the center of a sphere to a point, all of these lines that I just drew, we could consider the radius. It's the distance from the center to the edge. We can also measure all the way across, just like we did with a circle. And that would be considered the diameter. So just like with a circle, a sphere also has a radius and a diameter. And so that wraps up our conversation about points or figures in space. We had different types of three-dimensional figures. We talked about planes and also these polyhedra. And so that that does wrap up everything from chapter 10, geometry.